Welcome to where we are putting together solutions for students who are having problems in the area of primary mathematics. And in this video, we'll be looking at the secondary entrance assessment, or the SEA, and specifically the one that came in 2024. Because students are struggling so badly, the length of the video has to be cut down, so we are only doing section 1 in this video. Don't forget to like the video and add any comments down below so that we can help you by creating other videos in the areas that you are struggling with. We also have channels for the CXC Mathematics at Form 5 and for the CXC Additional Mathematics for students who are getting problems. So now let's look at the distribution of questions. In section 1, it is broken up into 4 strands. The first strand is number. Number takes up almost half of the objectives that has to be covered in Standard 415. So out of this section 120 questions, half of the questions from numbers 1 to 10 will be on number. And then on measurement, we'll get the next 4 questions from 11 to 14. And then from there, we will be going on to geometry, which has 3 questions. And statistics, which takes up the last 3 questions as well. So that would cover all 20 questions. Let's go on now to number 1. And as we look at that question here, which of course falls under the strand of number, write the numeral for 230,563. And of course, some students can do this automatically, and that's fine. But we would just want to have a little revision in how we can approach this question. I'm sure your teachers would have done this many times in class, where they set up the place value chart. And of course, on the right side is ones. And what comes next? Tens. And what follows? Hundreds. And of course, we can repeat that because math is patterns. So what comes after ones and tens and hundreds? Well, ones and tens and then hundreds. And if we had to repeat that for even larger numbers, right now we have 1, 2, 3, 4, 5, 6 numbers. If we needed more numbers than 6, then the pattern would repeat again, ones and tens and hundreds. And if it got even larger, it would still be ones and tens and hundreds. So let's clarify this. The first 3 letters or place values were all under the idea of ones. That's what the family is, or the period. And the next 3 places, ones, tens, and hundreds, would be under the family of thousands. And if we had to go further, then what would come next? Millions. Ones and tens and hundreds of millions. And even if we had to go further, then it would be even billions. Now, students easily see this because they recognize that math is patterns, and your teachers would have shown you that. So let's look at the question now. And what do we want to find? We want to look at the numeral dealing with thousands first of all. So thousands will be in this first category here. And how much thousands? 230 of those. So how many hundreds? 2 hundreds. 30 means how many tens? 3 tens. And of course, 0 ones, 230. And most students can easily work out a 3-digit number. So 230, 230. And the rest of it will be, knowing that we have 230,000 now, will be to look at the 563. So how many hundreds do we have? 5 hundreds. How many tens do we have? 60 means 6 tens, and 3 means 3 ones. So that's our answer. Or we could look at it separately, 230,000 and 563. And if we do the basic addition here, we can easily see that is going to give us the 3 ones, 6 tens, 5 hundreds, 0 thousands, 3 tens of thousands, 230,563. Let's now move on to the next question now. In number 2, write the value of the underlined digit in the numeral below. So we have 9, 5, 3, 6, 7, and the 5 is underlined. And we could use a different approach, right? Let's look at the place value chart again. And of course, we have ones, tens, hundreds, O-T-H, and it's repeated again, O-T-H. And what did we say the first 3 were? Ones, and the next 3 were thousands. And some teachers use place value discs to represent these. So if we look at the 7, that 7 is 7 ones. So you will see that some of them they cut out the circles with ones written on them, or they have little foam circles or ovals or squares, indicating that we have 7 ones. It shows us the value. Now let's look at 6 tens. So the place value is tens, and we have 6 of those. So we can pick up 1 10, 2 tens, 3 tens, 4, 5, 6. So we have 6 of those. And now what do we have following? We're dealing with hundreds. How many hundreds do we have? 100, 200, 300s. So we can easily see the difference in the values. And now we have 5. That will be thousands, 1,000, another 1,000, 3, 4, 5. And of course, 9. That would be tens of thousands. So we bring up enough of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can clearly see that the 9 represents 9 10,000s or 90,000. And look at our question. It's asking us for what is underlined, which is the 5s. So we can see that it has 1,000, 2,000, 3, 4, 5,000. So the value of the underlined digit in the numeral below is 5,000. So we've used place value disc here to show such. Let's move on to the next number question here, number 3, where it's saying a common factor of 15 and 18 is 1. What other factor is common to 15 and 18? And there are many ways to do this, right? So let's look at the idea here of 15 squares connected to form a large rectangle. So if you notice there, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of them. And if we look at this rectangle, let's think of the dimensions. What is the length and the breadth? On one side, we'll get 1, and the other side, we'll have 15. So 1 by 15 will give us this area of 15. So the factors of 15 are, factors would mean like what is the length and the breadth? 1 and 15. Now let's look at these 15 squares we have there. Can we rearrange them to get another rectangle? Well, let's look at the first 7. Let's bring it down. And let's bring the next 7, 8, 9, 10, 11, 12, 13, 14. And that gives us a rectangle right now. But did we use all 15 of those? We didn't. So when we bring this 15 here, this now does not give us a rectangle. So we cannot get factors from this shape. All right, so we tried 1 as the width. We tried 2. 2 doesn't work. Let's try 3. So if we have 15 of them, we could bring down 5, and let's bring another 5, and we bring another 5. Does that give us a rectangle? Surely it does. So let's form this rectangle, and what do we know about the sides? One side is 3, and the other side is 5. So the factors of 15 are, we formed one large long rectangle, 1 by 15. We formed another rectangle, 3 by 5. Could we rearrange these 15 squares to get rectangles whose lengths are 4? Well, it'll give us 4, 8, 12, 16, not 15. So we can't get another rectangle being formed with these 15 squares. Let's do the same with 18. So let's bring up 18 squares down below. And if we have 18 of them, does that form a rectangle if we arrange them long? Yes, it does. And what are the dimensions of this rectangle? 1 by 18. So the factors of 18 are, because it forms a rectangle, are 1. And we can see here that 1 is the same in both of them. That's why in our first line, a common factor of 15 and 18 is 1. What's the other factor of that yellow and clear rectangle we formed below? Well, it's 18, 1 and 18. Could we rearrange this anymore to get another rectangle? Well, we have 1 to 9, and then we carry that across. Look, we're going to get a 9 on below and a 9 on top. So we have a rectangle here whose dimensions are 2 by 9. So the factors of 18 are 1 and 18 according to the first rectangle. When it's rearranged, it gives us 2 by 9. So we have 4 factors. Could we get any more? Let's look 1, 2, 3, 4, 5, 6, and come up straight to 18. Well, we tried 1 as the width, 2 now. What about if we bring out 6 of them here? And we bring another 6, 6 and 6 is 12. We're doing our 6 times table. And another 6 will give us 18. And we've used up all 18 squares. And it forms a rectangle. What's the rectangle dimensions? 3 by 6. So the factors of 18 are 1 and 18, 2 and 9, 3 and 6. So let's look at the question again. Could we get groups of 4? Well, 4, 8, 12, 16, 20. Doesn't give us 18, we won't have enough. So those are all the factors there are of 15 and 18. So what are the common factors? 1, which was already stated, and the question asks, what is the other common factor? What's the same in both of them? Well, 3. So 3 is the other common factor of 15 and 18. Let's move on. And we're looking at number 4 now. Write one of the following symbols in the box below to make the number sentence correct. So we have 8693, 8,693 is either greater than, equal to, or less than 8,639. So let's just recall which one is the less than sign. We know the equal sign. So let's extract this here. And if we extend it a little bit, it looks sort of like an L. So if we form our hands like that, with our thumbs together, we can see a L being formed. So that is our left hand. And similarly, if it's our left hand, let's extract it and make it larger again. Then the left hand indicates less than. So our symbols are either greater than, equal to, or less than. So which of the 3 is it? So what we can do, there are so many different ways to do this. We can just indicate with a number line, 8,500, 8,600, 700, 8,800, because we know we're all in thousands and counting in hundreds. Now let's look at the two numbers. Both numbers are 8,000. Both numbers are 600. So we have 8,600. And what comes after? 8,700. So let's put a benchmark. Let's put something in the middle of it. What lies directly between 8,600 and 8,700? Well, 8,650. So if we know that, let's look at the number on the left side. 8,693. Will that be below that purple line or above? Well, it will be above. So that gives us 8,693 is above or more than the benchmark. And what about 8,639? Is that the same as 50, more or less? It will be lower than. So 8,639 is less than that. So if we compare the two, 8,693 is more than 8,639. That's good. Now let's go on to the next one. In number 5, we're going to have a division where 9 is divided by 927. That's all the question gave. They're asking us to solve. There's so many ways to solve it using long division and so forth. So let's look at it a little bit. 927. So 900s. Let's bring up a base 10 blocks and we see the squares here. And those squares, 10 by 10 squares, indicates 100. And how many of those hundreds do we need? We need 9 of those. So we have 900. And then how many, what does that 2 represent? 2 tens. So we have 10 and 10, 2 tens, and 7 ones. Now, what does it mean to divide by 9? 9 into 927. So teachers say 9 into 9 is 1. Well, what it really means is that we have 9 squares here. Can we form a group of 9? Yes, we can. We can form one group of 9 squares. So that will give us 1 square or 100. And then can we look at the 2 tens? Can we take those 2 tens and form groups of 9? No, we don't. We don't have enough of the tens. So it will be 0. Now, we can't handle the tens. Can we change 1 10 and replace it with 10 ones? And then take the next 10 and replace it with 10 ones? Now, how much do we have? 10 and 10, 20 and 7, 27. Can we form a group of 9 there? Well, yes, we could get one group of 9 out of those 27 blocks. Can we get another group of 9? You can count it. 3 and 3, 6 and 3, 9. So we're getting 2 groups of 9 out of those 27. What about the remainder? We have 5 and 4, 9. So we can form 3 groups of 9 from that 27. So our answer is 103. Other students would prefer that we could just take the 927, break it up into parts. Right? So we could say 900. Let's look at that first. How many 9s can we get in 900? We can get 100, which is what we did with our big blue square that we put. One group of hundreds. And what is the remainder? The remainder is 27. So we have 927. How many groups of 9 can we get in 27? We can get 3 groups of 9. So we got 100 above and 3 more. So how many groups do we have in all? If we add down 3, 0, and 1, 103. So it's a different way of approaching the question. There's so many different ways of doing this, right? So now let's move on to number 6. In this fractions question, which falls under number, we have 7 minus 2/3, and we have to work out that. So there are different ways to do it. We can think of it as if we're looking at the denominator as 2/3, that means each whole has how many parts? 1, 2, 3 parts. And we have 2 wholes, 3 wholes, 4 wholes, 5 wholes, 6 wholes, 7 wholes. Good. So now that we know that, we have 7 holes here, each hole has 3 parts, we can now minus 2 of those parts, or 2/3. So when we look at it visually here, we can easily see what is our answer. We have 1, 2, 3, 4, 5, 6 holes, and 1 little part remain. So 6 and 1/3, and the question is finished. If you want, you can tackle it a different way. Some teachers will say, well, we could take the 7 and break it up into 6 plus 1 is 7 minus 2/3. Right? And we have the 6, and we're working 1 minus 2/3. So we have to take the 1 and convert it to how many thirds? Different ways to do it. I'll use it using our multiplication tables. We are accustomed to looking at our tables here. And let's look at our 1 times table. 1, 1 is 1, 2 is 2, 1, 3 is 3, and so forth. So we have 1 whole. 1 whole is 1 over 1. That's the same as 3 over 3. That's what our multiplication table says when we slide it down. So we can replace 6 plus 1 minus 2/3 by 6 plus 3/3 minus 2/3. And we have 3/3 minus 2/3 will be 1/3. So answer is also given as 6 plus 1/3 there, or 6 1/3. Some people like to use a number line instead, 5, 6, 7, 8. And we're looking at the questions. Let's look at 6 and 7. Let's expand it a little bit so it'll be easier for us to see. And we're counting in the fractions of thirds. So if we start with 6, we'll have 6 and 1/3, and we'll have 6 and 2/3, and then we'll have 7. So if we look at the question up on top, 7, let's indicate that minus 2/3. It means we're going to the left. 1/3, 2/3. So we have moved 2/3 to the left. And what are we ending up with? 6 and 1/3. So 3 different ways of looking at this question. Let's move on now to number 7. Write 0.40 as a fraction in its lowest terms. So let's look at the place value chart again. 0.40. Well, the first 0 on the left-hand side indicates it's a whole number. So that is ones. And with the decimal point, let's bring up a square to represent ones or wholes, right? And let's look at the decimal point now. What does that indicate? Something smaller than ones. So that is tenths. So what can we do with that whole? We can cut it up into 10 parts. And what does 4/10 indicate? It means we have 1, 2, 3, 4. 4/10. And what comes next? Hundredths. So if we had 10 parts, how do you get 100 parts? Just like looking at the base 10 blocks. We can add 10 going across. So we're going to have 10 tens, which is 1/100ths, makes up the whole. So we can say that 0.40 is really 10 fours are 40 hundredths, or 40 over 100. Can look at the question. It says to reduce it to its lowest terms. So what can we do? Let's try and remove those extra 10 rows that we had. So we only have 10 columns. What does that tell us? Are we now counting in hundredths? No, we're not. We're counting in tenths. So how many tenths do we have? We have 10 tenths. And how many of those tenths are shaded? 4 out of those 10. So 4/10 is the same as 40 over 100, or it's the same as 0.40. Some people prefer to work from 40 over 100 and say whatever we do on top, we do below. 1, 2. So we divide by 10 on top. 40 divided by 10 is 4. So 100 divided by 10 is 10. So we get 4/10. Is that to its lowest terms? Well, if we look at 4 and 10, both of them are even numbers. So they may be able to get even smaller. So let's consider now grouping those tenths or those columns that we have. So let's put each put pairs to form a shape. So now what do we have? We have 1, 2, 3, 4, 5 of those. 5 of those rectangles, which are indicated with a red border. And how many of those are shaded? So we move from 10/10ths to fifths. How many fifths? 5 fifths. So we move from hundredths to tenths to fifths. And this is how we reduce to its lowest terms. And how many of those fifths are shaded? Well, that's easy. We could read it off. And it will tell us we divide by 2 on top and we divide by 2 below. So we get 2 fifths. And we can see that from the diagram that 2 out of 5 parts are shaded. That's the lowest terms. Let's go on now to number 8, where it's a multiplication question, 3.12 times 4. And there are many, many different ways to do this. So I'll look at it as if it was an area question. And we could take the 3.12 and split it up into 3 wholes and 0.12 as one side and 4 as the other side. So we could look at the first rectangle here, which is 4 by 3. And another rectangle here, which is 4 by 0.12. So I'm imagining this is like a measurement question. If we picture the idea of our place value chart, we have ones. And we have how many ones? 1, 2, 3, right? And then what comes next? We have a decimal point because we have tenths. We have 1/10. And we have hundredths. How many hundredths do we have? 1, 2. So if we consider now we want to multiply that by 4, then we have one pair and we add a second pair and we add a third pair in the hundredths column and we add a fourth pair. So what do we have? 1, 2, 3, 4, 5, 6, 7, 8. 4 twos are 8 hundredths. And we have to do the same thing for tenths. 1, 2, 3, 4. 4 sets of them we want. So that tells us that we have 0.48. 4 times 0.12 is 0.48. And let's deal with the ones now. We have to get how many of those threes? 4 groups of threes. 1 group, 2 groups, 3 groups, 4 groups. And of course, we could group 10 of those ones together and replace it, and that will give us 110. So we left with 110 and 2 ones, which is 12. So our answer is 12.48. There's a different way of doing it. I know you have shorter ways to do it on this as well, but in case you get in problems, you want to look at it and we can picture what is happening. Let's go on now to number 9, where they're asking us with a percentage question to calculate 15% of 300. And there are so many ways to do this. Let's picture a number line, 0%, 10%, 20%, going up the road until we reach 100%. 100% is all. So calculate 15% of all. And what is all? All, or 100%, is 300. So if we know 100% is 300, what is 10%? 1/10 of that. So that is 30. So we know 10% is 30. If we add another 10%, that will give us 20%. So 30 and 30 is 60. What do we want to find in our question? We want to find 15%. So we have 10% and 20%. 15% will be somewhere in the middle. What's in the middle at 30 and 60? 45. So that's it. We solved the question. We can also look at it as if it's a whole. 100% is equal to 300, or 1 whole is 300. We can break it up into 10 parts. So one of those parts, or 10%, is 30. And we know that 10% is 300 over 10. which we got 30. What to do now? If we draw a line across, we'll break that up, that 10% into a 5%. So we add a 5% to that 10% and 5%, it's 15%. So 5% will be half of the 30, which is 15. So if 10% is 30 and 5% is 15, 15% is equal to 30 and 15, which is 45. That's another way to work it out. And of course, there's the standard way where our teachers have shown us 15 over 100, so that's percent, out of 100, multiply by 300. We say how many hundreds can go into 100? 1. How many hundreds can go into 300? 3. And now we have 3 15s, and we know our 15 times table. Remember, our teachers would have shown us this. We have our clock. We start at 0, and 1 quarter turn, or 1 is 15 minutes has gone. 2 quarter turns is 2 15s are 30. And our question is 3 quarter turns, which is 45. So we've gotten our answer. 15% of 300 is 45. And just to show you our 15 times table, 4 quarter turns is 60. So we know our answer here. There are 3 different ways to solve this question. Let's now move on to number 10, the last of the number questions. An incomplete pattern is shown below. Let's look at the numbers 36, 28, 21, 15, something else, and then 6. So what is happening to all the numbers? They are getting smaller and smaller. It is a decreasing pattern. What's the question asking us? What is the missing element in the pattern? So if we want to look at that, let's bring up 10, 20, 30, 36. So we have 36 we're starting with. That's our first thing, and we're moving to 28. So what happened there? We minus 8. So let's bring that 8 across so you can see it. Let's put it one side. So if we move the 8 across, 36 on the left-hand side became 10, 20, 26, 27, 28. Now what happened next from 28? It went to 21. So we minus 7. Just now we minus 8, 28 minus 7 is 21. So let's move 7 across now. 2 and 5 is 7. So the first one was 8 we moved. Now we move 7. And what do you think we'll move next? 21 minus what number is 15? 21 minus 6. So let's see if that pattern makes sense. 5 and 1, 6. So we have 8, 7, 6. As you see on the right-hand side. So therefore, what do you think coming next? Well, we'll have to minus 5. So if we minus 5, so we're maintaining that pattern on the right side of the purple line. Then what is left? 6 and 4 is 10. So 10 is the missing element in the pattern. And just to see that it was making sense, what would move across to the right-hand side now? We moved 8, then 7, then 6, then 5. Now we would move 4. And if we move that 4, we'd be left with 6. And that's it. That shows the pattern. Let's now look at number 11, where we moved out of the number strand into our measurement. What is the length of the pencil in centimeters? There are many ways to do this. One way, we can put a starting point here showing 2 centimeters is where it starts. I like to bring up a ruler and then slide the ruler across until it reaches 0. And if we count it until the end, which is purple, we will see there from where it starts 0, 1, 2, 3, 4, 5, 6, 7. It's 7 centimeters long. So that's our answer. Some people like to say, well, it ended at 9 and it started at 2. So 9 minus 2 is 7. And that will work as well. That's fine. Let's move on to the second question in the strand, number 12. This time question says, Aiden left home at 6:45 a.m. and arrived at school at 7:25 a.m. How long was his journey? So there are many different ways to do this. Let me bring up an analog clock. And let's start at 6:45. If it's 6:45 a.m. is where he's starting, the hour hand will not be quite at 7 yet, but it'll be close to it. So it'll be between 6 and 7. And the minute hand, we'll put that in red, will be at 45. 45 is what number? It's the number 9. And if we're moving, because Aiden left home at this time, and we move, the minute hand will go up to 12. And every time it moves up, it'll go 5 minutes, 10 minutes, 15 minutes. By that time, it's 7 o'clock. And we want to move until it's 7:25. By that time, the red hand will reach at what number? It will reach the 5. So every time it's moved, we're adding 5 minutes. As we move to the 1, then it'll be 20, and then 25, 30, 35, 40. So how long was the journey? 40 minutes. Some people prefer to do it like a digital clock. It ended at 7:25 and it started at 6:45. So we could do some subtraction. 5 minus 5, that's 0. And 2 minus 4, that won't be possible. So we have to borrow from 1 hour. 7 hours minus 1 is 6 hours. And when we carry 1 hour across, how many 10-minute intervals are there? That makes an hour. 6 10-minute intervals. So we have 6 and 2, 8 10-minute intervals. 8 minus 4 is 4. And as such, our answer is 40 minutes. Let's go on now to number 13. A shaded shape is shown on the 1 centimeter grid below. Each square is 1 centimeter by 1 centimeter, or 1 square centimeter. What is the area of the shape? Well, the area of the shape is just the number of square centimeters that covers it. So we could cover it in green squares, 1, 2, 3, 4. So you can write out the area for the first line is how much? 4. One group of 4. And we can do for the second row, another group of 4. And for the third group, another group of 4. So right now, if that's all it was 3 4s, 4 and 4 and 4. Can we get another group of 4? Yes, we can. So we have 4 4s so far. That's 16. And what is happening here? We have a piece, and a piece, a half, and another half, and another half. Well, we could put them together. Let's slide one across on top there. That forms 1 square. And form that across another square. So we'll get 2 more. So what's the area? 4 and 4, 8, and 4, 12, and 4, 16, and 2, 18. 18 square centimeters. Let's go now into number 14. In number 14, 2 packs of sugar are shown below. 2.5 kilograms and 1,600 grams. So the question is asking us, what is the difference between their masses? Now look at the answer. They want their answer in grams. You can easily do this. Now see if you remember. If we bring up a scale and we want to balance the scale, on one side will be 1 kilogram. It's the same as 1,000 grams. Your teachers would have done this in class. This is a little revision for you. So if 1 kilogram is 1,000 grams, 2 kilograms will be 2,000 grams. 2.5 kilograms will be 2.5 times 1,000. And how do we multiply by 1,000? We shift the point one place, two places, three places to the right, because you have three zeros in the 1,000. So that will give us 2,500 grams. So the larger package of sugar is 2,500 grams. The smaller package of sugar is 1,600 grams. So what is the difference? It means we have to subtract 0 minus 0, 0 minus 0, 5 minus 6. We will not be able to do that yet. So we have to borrow from the 1,000 column. And then how many hundreds will that give us? It will give us 10 hundreds. 10 hundreds and 5 hundreds is 15 hundreds. 1500 minus 600 is 900. And 1 minus 1 is 0. As such, our answer is 900 grams. Let's move on now to number 15. Jillian is standing at O. O is the center of that diagram and facing northwest. She makes quarter turns and is now facing southeast. What is the least number of quarter turns made by Jillian? So let's bring up an arrow to show that Jillian is at O facing northwest. And she can make a quarter turn. We have that in blue, indicating one quarter turn, another quarter turn. So that is 2 quarter turns when she moved in that anti-clockwise direction. And if you check it in the other direction, if she moved in a clockwise direction from northwest to southeast, it will still give us 2 quarter turns or half a circle. Good. Let's go on to number 16 now, where we're looking at the idea of this shape. How many vertices are there in the solid shown below? So let's recall that if we have one side or one face meeting another face, when two faces meet, that forms an edge. When we have more than two faces meeting, then that will give us a vertex. So how many vertices, the plural of vertex, are shown below? Well, let's see. We have 3 edges meeting there. That's 1. We have 3 edges meeting in blue. That's 2. Let's look at the back one in green now. We have 3 vertices. And in red, we have the 4th vertice. And in green, we have a 5th vertice. Is that all? No, we have 1 more. And over here, we have 6. So there are 6 vertices in this shape. Let's move on now to number 17. We're almost done. Draw all of the lines of symmetry on the shape below. So they gave us an H. A line of symmetry or a mirror line or a line where we can fold it so that one side fits upon the other. If we look at drawing a line coming down, where could we put a line so that maybe we would be able to fold it along that line? We could put a line straight down the center. Now, is it able to fold there? Let's look at the left-hand side, look at the shape, and if we folded it and carried across, look, it will fold evenly. So there's one line of symmetry coming downwards. Let's take that off now. Are there any more lines of symmetry? Can we do one diagonally? Well, if we do diagonally, it won't fold and fit exactly on the other side. So what about horizontally or flat? If we fold that there, can we see a C or a U above it? And if we flip it over, well, are we going to get another U? Yes, we do. So as such, we have one line of symmetry going across and one going up and down. So there are 2 lines of symmetry. Let's move on to our last strand, which is statistics. So in number 18, the mean of 3 numbers is 12. 2 of the numbers is 10 and 11. What is the 3rd number? So we can make a little sketch here and bring it up. Let's draw a little rectangle and an average of where 10 is. That's the first number, and the second number is 11, so it's a little taller. Do we know the third number? We don't. But the mean or the average of these three numbers is 12, which means that if we were able to share the three numbers equally, they would all reach a height of 12. So let's draw a line there indicating where 12 would be. As such, in the first column where we have 10, we are a little short. How much do we need to reach 12? We need 2 more. In the blue column there, are we reaching 12? No, we're not. So we can add 1 more. And of course, the third column, which is in green, has to reach 12 as well. So we have a number 10, we have a number 11. What's the third number? Let's put them all together. Carry the 1 across, carry the 2 across. So that will give us 15. So that is our third number. Some teachers prefer to do it this way. Well, we have the average is 12. So we could say 12 threes, or we could add 12 and 12 and 12, and that will give us, of course, 36. And the total is 36. We can now take away the blue part. So 6 minus 1 is 5. 3 minus 1 is 2. So if we had 36 and all we're supposed to end up with, and we took away the 11, we would have 25. And if we take away the brown, 25 minus 10, and that will be 5 minus 0 is 5, and 2 minus 1 is 15. So that is one way teachers normally show students. I prefer the one on the right side so they could actually see what's happening. Let's now go on to number 19, our second statistics question. The tally chart below shows the types of gifts students received. So gifts, students got bicycles. We have 5, 6, 7, 8 of those. Books, 5 and 5. Cell phones, 5 and 5 and 5 and 2. Tablets, 5 and 5 and 5. So which gift represents the mode? Let's recall the mode, M-O-D-E, means the one which is M-O-S-T, most frequent, most regular. Which gifts were gotten the most? Well, you could easily tell without even counting that it's the cell phones, because that has more than any other one. So notice that which gift means that our mode is cell phones. It's not the number of cell phones. But if you wanted, we could check it. How many bicycles do we have? 5, 6, 7, 8. How many books do we have? 5 and 5, 10. How many cell phones? 5 and 5 and 5, 15, 16, 17. And how many tablets? 5 and 5, 10 and 5, 15. And 17 is the most. So cell phones is the most popular gift. Last question now, which is, of course, a statistics question. The pictograph below shows the colors of students' book bags. We have number of book bags. Red, black, blue, and brown are the colors of their book bags. And it says, if 32 of the book bags are black, how many are blue? So we had how many black book bags? 32 of them. And they're represented by the idea that there are 4 smiley faces. So 4 smiley faces tells us there are 32. So you can say 4 smiley faces equal to 32. 1 smiley face would be 32 divided by 4, which is 8 book bags. Do we have anything with 1 smiley face? Yes, we do. Look, the red is 8. So that's 8. And if you look at the black, 8 and 8, 16, and 8, 24, and 8, 32, right? What does the question ask us? If 32 of the book bags are black, how many are blue? So let's look at blue. How many smiley faces do we have? We have 3 smiley faces. So let's write that. 3 smiley faces is 3 times each one is 8 book bags. 3 eighths are 24 book bags. So this brings us to the end of section 1. We have now come to the end of SEA 2024. Past paper question. Section 1. We started doing Section 1 papers from right after during the COVID time, which is from SEA 2019. And we have done 2020, 21, 22, 23, 24. And our next paper will be SEA 2025. So thank you again. And I hope this shows you different methods and different ways to look at the mathematics and see that math is not something abstract, but it's something you can see and picture and feel and touch. Okay, bye.